Agora sim, ao vivo e a cores todo o Brasil. Bom dia, pessoal. Recebendo aqui o Roberto, e a professora Adriana vai fazer a abertura aqui, dando uma pequena biografia do Roberto. Obrigado, Adriana.
Obrigada, Gonçalo. Obrigada pela presença. Agradeço aqui a presença do Alexandre, vice-diretor da FAO, nessa abertura dessa primeira aula do professor Roberto, né, que faz parte do nosso ciclo 7 às quintas, Olhares do Mundo, ciclo Pro-Urb, o nosso quarto encontro desse semestre. O professor Roberto vai proferir a palestra Wood Innovation for Architecture in Brazil. Roberto Naboni é um arquiteto experimental e professor associado em Design Computacional e Fabricação Digital na SDU Southern Denmark University, liderando o Create Lab desde 2018. Formou-se com honras no Politécnico di Milano, onde cofundou o ACTLAB, focado na computação arquitetônica. Sua pesquisa integra novos sistemas de materiais e manufatura avançada. Colaborou com centros de pesquisa e escritórios internacionais, incluindo a ICD e ITKE Stuttgart, AA School, Skidmore Owings and Merrill, Enric Miralles e Benedetta Tagliabue, associados, e Stefano Boeri Studio. Roberto Naboni, thanks for being here. The mic is yours.
Okay, thank you. Can you hear me like this?
Yes.
Okay.
But we need the microphone.
Okay, but I can. Okay, thanks for the introduction. Thanks for the invite to be here as a visiting lecturer for this term. How much time do you have? Because we are starting 30 minutes later. Okay, I will try to keep it as short as possible. I think 1 hour could be a bit long because we're starting a little bit late. Anyways. So, thanks again for the introduction. I'm not going to repeat that. So, I'm an associate professor in computational design and digital fabrication, and I'm leading a research center which is called SDU-Create. Today, I'm going to talk about automating architecture and the building environment, and I will try to get you a little bit of a journey of some of the projects we've been doing over the last year in my center, and I will focus especially on wood architecture. So, very briefly, this is the center that I'm leading. We look into computational research in emergent architectural technology and engineering. I know here is Faculty of Architecture and Urbanism, so we do work across architecture and engineering. I like to think that design engineering is a continuous process. So we show to you some quite technical work as well. Okay, that's interesting. So, this is basically where we are located in Denmark. The building that you see here on the left is basically our headquarters, it's Faculty of Engineering in Odense, and basically this is Block Sub, which is our presence in Copenhagen. And why I'm showing this is a little bit to put you a little bit in the context of Denmark. Odense is considered to be the capital of robotics in the Nordics, in Northern Europe. We've been this morning looking into how to use collaborative robots. You've been looking into, some of you, playing with a universal robot. Actually, universal robot, it is a product, a spin-off from our university. So, it used to be just a couple of students playing basically in a lab, and then became like a huge company. Now is American owned. Copenhagen is the capital of architecture in general, so we work across these two worlds and we try to connect basically the best of technology with the best of architecture. The work I'm going to show is not my personal work only, actually represents a team that is behind. We have about 14 researchers at this point. We have postdoc, PhD students, research assistants. Very often we have visiting PhDs. And it's very important to show this because the team is made by very talented, smart researchers, but also it is interdisciplinary. As you can see here, some of the topics we work on, but something to mention that is not super explicit here is that there are architects, building engineers, experts in robotics, mechanical engineering, So that is the kind of work that we work with. But despite this introduction, something important to mention is why we're doing research, and I'm pretty sure you hear a lot about sustainable design and how we should solve some of the emerging problems, actually not so emerging problems anymore, that we have in our field. Just very briefly to remind you, we are responsible as built environment for 39% of carbon emission, a huge share of extracting natural resources, and huge waste generation. So we are called these days to cut down all of these, especially we have strong policy in Europe, but in the whole world in cutting down carbon emissions from construction, while we have to provide much more buildings, houses, infrastructure for a growing population worldwide, which will grow over the next decades for 2 billion more people. So in our center in Create, we do work with different areas, from 3D printing, 3D concrete printing. We work with also soil-based kind of explorations, and timber architecture, and other fields that are not represented here. I can a little bit generalize saying that we work with 3 main material systems, which are polymers, concrete, and wood. A lot of the polymers are actually biopolymers. So there is a somewhat an attention to the technology we use, but also the materials that we focus on, because after all, you cannot be expert of everything. So we focus today on timber, and why do we focus on timber in general in our research is because we look at timber as a carbon store. So nearly 50% of the makeup of any part of wood that you can find is basically carbon, which is fixated. And you could look at wood as the equivalent of 1 kilo of wood have basically embodied 1.8 kilograms of CO2. So it's very important to look at this.
This is really annoying.
Can you hear the sound as well?
Yes.
Okay, it's a bit distracting, but I will make my best.
Want
So-
to try the other one?
Yeah.
Is this better? Oh yeah, it is better. Okay, fantastic, yeah. Okay, so we're looking into timber. Timber is of course a renewable material. It's very important. There is probably all of you has experience working it through your education and research. The way that we like to think of timber is as a carbon storage, so something that can actually help us avoiding emissions. However, the idea that we can build everything out of timber is very naive. There is not just an ecosystem that can support that. Forests are not an infinite resources. We need much more building materials than what we can provide with existing forestry. But I invite you to look at it as basically a sort of larger carbon sink made out of forests and wood buildings. So whenever you build out of timber, you're actually storing carbon until this basically it gets unused. So this is very important because you don't only want to offset your, let's say, carbon emissions, but you want to preserve, to store them for long. And therefore we need to think on how to keep basically wood in the construction value chain for longer. That's why we focus on extended wood life cycles, because that's key to decarbonation. How do we do that? And basically the presentation will revolve around these concepts is by enhancing circularity. Something we've been working a lot with is structures that can be assembled, disassembled. We call them reconfigurable structures because they can facilitate this process. Another important factor that we look into is basically into reducing or eliminating waste. So building components that are designed for multiple life cycles already, but of course the goal is increasing carbon storage. So this is a very quick introduction about the topic, but I'm going to show you now some of the projects. It's a little bit chronological, so you can see also a little bit of the evolution we've been doing over the last years. We started looking into this concept of versatility with this project, which is called Reversible Robotic Timber Beam. And the idea here was to look into assembling wood parts that could actually be reused. So this is basically the final outcome, is this sort of beam that is a couple of meters in length, and the idea was to make such a complex design, not out of very custom parts, but actually parts that are generic, such as these ones. So these were basically the parts making a construction component. This construction component was sort of Lego inspired, which means they could be actually processed and manufactured in large scale as mass production using industrial CNC, and then basically the specifics of the design would actually get because of the placement and the use of robots and some design strategies that I'm going to show you. In this project, we have been actually using for the first time collaborative robots to put wood structures together, not only as pick and placing, so what we are going to work on over the next days, as you can see here with this gripper, which is very similar to the system that you're going to use over the next days, but also installing an electric screwdriver, which was mounted basically as a sort of complementary tool. And this is, at least to our knowledge, the first case of a fully assembled architectural component made out of timber by robots. Now, the topic is a little bit about automating. Automating is not only automating construction, but automating design, and that's extremely important because it allows us to basically develop workflows that can be reproducible, that can be picked by others, and that can be effective and can be also repeated and improved by time. So this is a little bit one of the many diagrams that we use actually to show how we develop our projects. On the left side here you see everything that we consider design, and on the right side is everything that we consider construction. You see here we talk about digital twins for design and robotic assembly. I will get back to that in a minute. But a very important point here is that we want to create this digital continuum, and it's extremely important because these specific parts or these specific beams can only be made once. They cannot be made as a repetitive product by robots, but actually they need to receive parametric information from a modeling environment. So how do we design these things? Essentially, we generate a lot of these workflows where we look at the stress patterns, how stresses actually move around within a structure, and how these can be actually discretized into parts, voxelized as we say, and this actually can be then computed further to understand exactly how this load path can actually be managed from loading conditions to different supports and so on. So we have this kind of general digital description of our construction elements, and then as you can see here there is basically ways where we can consider how to organize basically wood parts following the stress lines. So this is a little video showing a little bit how we put together such a structure. We're basically picking parts from this sort of magazines and then just placing them in the right place with two robots working in two different workspaces, but collaborating and overlapping to some extent, and then basically switching to this where we would actually place these screws. Of course, there is a little bit of building technology behind. There is some integrated connectors into these elements. But these first experiments basically allow us to prove that actually we can make such structures that are reversible. So this actually has been taken apart a couple of times and put together again. And following this initial study, what we focused on essentially is into developing a system in terms of robotic development that would be more resilient. And what we understood from such system is that you need high precision, you need actually to have robots that can adapt to different uncertainties, because wood is a material that is not perfect, and therefore what we started doing is actually integrating more feedback. What does it mean? We started on the same setup adding cameras, and with these cameras we were able actually to track where elements are and where this can, how to mount them. So this is a little bit nerdy, and this is a little bit the step where we develop robotic workflows. So what we did, we started using cameras to track where actually these screws has to be placed, so that this structure would be consistently put together, because what I did not show is that there is some degree of failure when you do this. So how to do this? Basically we need to create feedback loops. So this means that when we actually assemble the structure, maybe this gets a little more clear, we pick a block for assembly, we detect basically where are the holes where to put the screws, and then basically this update a model, and then the robot knows where to go and screw this. Otherwise, most of these redundant structures with many parts would fail. Because of this, what we could do is actually reverse the process and essentially started disassembling, because we would have already developed computer vision techniques to actually detect these holes, these screws, and therefore we could use the same setup for disassembling structure. So this is a small demonstration that we made, where we started basically putting together these structures and then disassembling and continuing this infinite loop, you could say. What happens in the background is something like this. So you have your digital design where you have some coordinates where the robot should actually place the screws, and this is basically what happens after scanning. So these are coordinated, corrected coordinates. This is where the digital twin comes to place, right? Because you have a digital model, you scan, you keep updating, and this is the difference between having a static model and digital twin. So this become now from an offline program, which is also what we're going to experience in the workshop this week, to an online program. This means that we connect digital models, robots, and structures, and now we have an idea of what's going on to some extent. Now, this allows us to basically view these many structures. The complexity here is that most of them are open in cells, so actually they can have rotations and so on. So just to make it a little bit more clear with data, nearly all of the structure wouldn't be able to be assembled without having camera vision, without having this correction I was telling you before. So these were basically early experiments which led to the development of what we call now Recombut system. So Recombut system is building up on this early research, and we have three pillars. The first one is tectonics. Recombut is a system for multi-resolution of wood framing, which are based on construction kit of reusable wood elements. So this was an evolution of what you've seen before. The second pillar is having cyber-physical construction. So these are structures that are designed to be automatically assembled, disassembled, reassembled through cyber-physical systems, which means basically using robots or using mixed reality, something that is basically allowing you to connect digital models to physical operational space. And the third pillar is using data. So since we are discussing as a topic the idea of reusing elements and circularity in construction, one thing that we understood for our research is that if you have no data about your elements or your structure, basically you cannot really activate and enable circularity completely. So I'm going to go very quickly through some of the prototypes we developed with this system, Recombut Proto 1. Here the idea was to design a sort of wall frame system using mixed reality in a sort of collaborative mode. Imagine basically like pulling points through mixed reality. This was very simple and exercise, you could say. And then producing elements with robotic fabrication and then looking into mixed reality for assembly. Here we started working into the idea of assembling the very same structures with mixed reality and thinking, okay, can this structure be as inclusive for robots and humans? So here's a little bit some of the preview that you would see in the user interface in assembling the structures, and essentially this is what you get out of it. So this timber framing, and here the multi-resolution goes to the fact that you could have very large elements or small elements with placing a lot of material or less material according to your needs, but also kind of developing this sort of shear interlocking, these features that allow the assembly to be easier and to kind of self-reference, but also have a mechanical feature as well. Then we evolved with this Recombut Process 02. We've been looking into understanding a little bit what would be our way of keeping data in the loop. So these are concepts that we look into. I don't know if you're familiar with material passports. That's something that we speak a lot about in Europe. So essentially implementing information about the origin and the history of the material. Normally what happens is that when you want to reuse materials from construction sites, you build sort of a material passport. And we've been looking into these concepts and we found out that essentially there is a lack of information when you want to reuse construction elements. So we built what we call now a material digital twin, which is our version of enabling circularity for data. And this is based based on a couple of principles. The first one is that this is a dynamic material database. So the database is not a static element that is somewhere stored, but it's something that can be continuously updated. It has a permanent link between material data and specific building materials, and that's why we use QR code, so that you can always reference elements back and forth. And it's bidirectional. This means that information can go from computation environment to actually structures, but also can be the reverse. And should be easily accessible, so it should be equally accessible by robots and human operators. So this material digital twin contains several levels of information about fabrication, assembly, use and operation, robotic assembly. And we've been using this actually to build this mini structure, which is an evolution of this recombinant system. But now I want to focus a little bit on the information level that you have behind this. So these are some of the categories of the information that is stored. So for example, we run finite element analysis to understand how much elements are actually stressed and so on. When you want to reuse construction elements that are made of timber, you don't want to stress elements to the limits because you want to favor reusability. So the information about basically the limit state of these elements are actually stored into a category for structural performance. So you have actually this information about material, the species, grade, density, weight, tensile strength, and so on. So all this information are stored because this data that can be used when you design the structures. Then, how do we produce the elements is also basically stored in the material digital twin. This is just to show you how these individual elements are fabricated. It is through this large setup for robotic milling. So there are different tools, as you can see, that are used. One that is like a typical hand mills. This is like a V-shaped tool. So there is actually quite some time that it takes to figure out these things, unless you are a very experienced CNC operator. All this information about the tools that are being used and so on are also part, essentially, of the information that we store in such a digital twin, as you can see here. So the idea is not only to operate on materials and structures with these technologies, which are to some extent quite known at this point, but is about keeping this information in the loop, having a consistent way of storing information so that can be reused later if you want to reprocess, for example, this element. One more layer is the layer of assembly. So we had several iterations of updating our setup, and in the Recompute Proto 02, we've been looking actually at collaborative construction between humans and robots. So this is a little bit of schematization of it. And here you see basically in the background all the information about the instructions that is projected, or you can see actually from mixed reality. So what did we do here is exploring the collaborative aspect of these robots. So these elements are generic. What the human operator is doing here is actually embedding nuts for the specific structure, and then these are placed in the right position. And then the two robots, which are cooperating, are actually placing together some of these modules. So there is a part where these elements at the beginning are mass-produced, then they get, because of the specific design, customized, so they get these nuts embedded, and then they're placed in the right place in the structure. This information is also stored here. So where are these nuts that are added? Well, they are also stored here. Now, long story to say that if you have basically your scanner or just a phone, you can interrogate each of these single elements and basically get to a database where you find this information. And that's fundamental, because if you want to do more computational design, more cycles of design and reusing these elements, you need to have the data available. So this is how it works. Basically, you can interrogate the structure in different ways, of course. And that's basically what you have. So a sort of visualization of all this data. This is a speckle model line. This is actually the previous database that we were using. Now we've actually implemented a new system. It's not here in the presentation because it's not published material yet. But essentially we have robots that are also updating the statistics, and I will show you just an image later. So we have extended this system for reconfigurable structure to horizontal structure, so looking into slabs, floors. And that's something that it's kind of important because it is a test bed for structural components. So here is the problem. When we look into timber architecture, most of the timber construction we're looking at today is engineered timber, so CLT elements like this. I don't know if that's also the case here in South America, but in Europe, timber architecture is this. Panels that are over-dimensioned, used for walls, used for floor systems, and that's it. So there is such an excessive use of material. We thought, can we actually use timber framing also for these horizontal elements? So we look into these recon slabs, always using the same approach, but now extended the construction kit also for other type of stresses. So this is a little bit how the system looks like at this point. So still using the same elements, but to some extent we basically kind of extended the sectional height of these and then looking into other type of connections that would allow us to put the same elements together, but now in new configurations. We have established a workflow where we look into form, shape, and material. We look into boundary conditions. A lot of our design processes in timber, but also other materials, they always start from some early front-end elements. So we look at performance, how things behave, and then we design parameterizing those. So this is basically a little bit the behind the curtains of the process. We look into voxelization of these elements. So this is the same approach that I showed initially in that beam. So we try to basically consider this into voxel elements, and we store at the voxel elements basically the trajectories for stresses, the main principal stresses, but also the stress magnitude. So that's a convenient way of computing these elements before they become wood elements in the system. And then we have a process where we basically materialize this into beam elements. And how to do this is running finite elements, basically structural simulation on the voxel themselves. And that, from a computational perspective, allows you to use much less computational power and do it much more efficiently. So, just to give you an example, so this is basically how it all starts. So we start basically with a random allocation of these voxels, and then we run iteratively the structural simulation, and the structure gets iteratively subdivided so that more material it is added. But as you can see, it's not added with the same orthogonal grid, but it's looking at this stress distribution, which is specific for the conditions that you have, so that it gets to a specific kind of layout. What happens to the material level? So this is what we call maxillization process. That's where we make a voxel, a sort of material voxel. That's the name maxil. We look essentially at each of these cells, how the stress are actually distributing over there, and then we look at extend, basically making this kind of edges becoming beams that are part of the recomposed systems. So in this process we look basically for neighboring conditions, and we try to associate conditions that are of the same type so that we can actually generalize this from voxels to structural elements that have continuity. So this is a little bit what happens, and this is how you get to something like this, just looking at that specific cells. When it is evaluated that the boundary conditions are actually the same, the neighboring conditions, these get extended, and then you get basically your hierarchy of elements and how this automatically become actually a list of beams. This also includes the connectivity of this. There is a lot of detailing, and actually the complicated part here is the construction sequence, which is not so easy to figure out. So this is a little bit how this works through different elements. But an interesting and powerful thing here is that you can use this approach because it is automated and because it becomes a computational workflow that can be reused. You can play around with moving different kind of supports, and this over time will give you a different kind of structure that is optimized for the specific case. That's the idea. So what you've just seen is basically this scenario, which here you see assembled completely by mixed reality. These are just some of the pictures, impressions of the structure itself. So we don't use boards in this case. We use basically primary, secondary elements. It is basically calculated to Eurocode, which is basically the structural code that we use in Europe. So the limit for serviceability, which means the deflection you can get on these elements, are actually fulfilling the requirement. So there are some images basically of the whole project, and there's some informal structural testing done on the structure. Do you have more time? Do you still have it? Or you are hungry for lunch?
Okay.
Okay.
10 minutes, 5 minutes, 5 to 10.
Well, so what we are building right now with this system is essentially something like this. We just have to assemble this. We have already produced all the parts all together. Now, this is the evolution, is material we haven't published yet, but essentially now the setup looks like this. So these are basically modules that are put together by these two robots that cooperate. What you see in the background is the database I was telling you before. So we do record a high level of information from how much does it take to screw each of these elements, how to pick it, and so on. So we have a lot of data, and that's very useful because it tells you how can you improve the system. So I suggest you look in future for publication that soon will be out about this. It's very interesting. But basically what we do with robots, we put together these sub-assemblies, and then these are put together in such elements like this. So this is one of the walls that are part of the structure themselves. And the interesting thing is that all these elements can be reused, as we said since the beginning, a number of times. We haven't done durability study, but potentially can be reused infinitely, right? Depends on how you treat them. All right. So I have many more slides, but I can decide what to show you. I think we can have another project. So we've been discussing on how to preserve food that is new or perhaps reused more into the construction value chain. Now I want to show you another project where we look into how to reuse wood that comes from construction waste. So this is basically coming from an idea that in Denmark specifically we have 4.5 million of tons of waste from construction every year, and 55,000 tons of timber is actually from coming from construction sites. So can we reuse, according to what I said at the beginning, can we extend the life cycle of this wood? Otherwise it's not a carbon storage. In a moment this gets basically burned, incinerated, or get rotten, all the carbon is actually re-emitted to the atmosphere. So you just offset for some years. So we've been looking to some data, and we figure out most of the timber that is going into waste facilities is actually burned. Very few is recycled, but are actually for particle board, which means that you lose all the properties of the wood themselves and use them just as fibers. But what we figure out that any element that is shorter than 80 centimeters goes completely incinerated directly. So we came up with this idea of boxlam, so reclaiming timber through voxels, and these voxels are actually laminated in some three-dimensional structures. So this is where we start from. So this is wood that is collected. You can see this all looks differently. You have no idea what's going on, what kind of type of wood is this. You have some idea about what is the structural performance there. It is kind of unknown. And then we look into topology optimization to essentially come up with these three-dimensional structures that are optimized. I don't know how familiar you are with topology optimization, but essentially, especially through this SIMP method, which is solid isotropic material penalization, you basically assign a sort of volume of material, and you allow this to be essentially moved around through gradients of material, which means certain parts, these white ones, of this will actually be where you want to have more material because of stress analysis, and basically these black areas where you want actually to limit the material if you want to make the structure more efficient. So we went through this process of collecting this dirty material, cleaning, planing, classifying this according to visual characteristics, and then running what we call stock and flow material layout. So you have material that is classified according to their density. The density of wood tells you some information about the strength of the material. It's directly proportional. So according to the availability of high density or low density material, you can actually optimize your structure in different ways. And finally, how to realize this design is transforming all of these small elements into continuous structures. So we've been running a test, small test, to understand what's the strength of these elements. So this is a sort of mini beam, and then we came up with this design for a sort of a truss, which we call now the voxel truss. As you can see here, there is a similar approach. We're always looking into voxels, and voxels are always useful for us for storing information about the material and the stresses. And then we cluster them according basically to, again, the neighboring cells. If they are basically have similar conditions, you can classify them and you can cluster them together so they can use larger elements. So this is a little bit an evolution of the truss that we've been developing through all these layers and so on. So all these elements, it's a sort of additive process, and this is how we basically made a structure that essentially looks like this at the end. So this is a fully structural element. Truss is lightweight, all of it is reused timber from construction waste, and this is basically new technology for lamination that we've kind of introduced and developed. But the most interesting thing here is that these are basically the length of the elements that we've been using, so, and their distribution. So most of the elements are actually of this size, and now I think up to 48%. But we've been able, in total, to reuse 95% of the material that we got from the waste. So completely random container of material, we've been able to use 95% of it. And the rest was completely unusable because it was rotten and so on. So that gives you a little bit an idea of the efficiency that you can achieve with these systems. Now, currently we're looking into upscaling this process from this that was actually put together a couple of graduate students for their master thesis. Now we're essentially looking into a process where all these elements are placed with a robotic tool. And there is something about the kind of connection. So here we're looking with structural glue, now we're looking into lignin-based essentially way of connecting these voxels, as it shows there. So this is actually an image that comes directly from a foundry application that we sent out. And the idea is that we can really have very lightweight structures that are topologically optimized, made out of timber. That's a completely new idea. So this was the last project I want to show you, and I just want to maybe point out 3 areas where I think we're going to work on ourselves, but I think anyone should focus on for the next years. So the first one is about digital rematerials. So looking into repurposing, classification, and assessing of reclaimed timber through non-destructive analysis and machine learning. The big question when you use material that you haven't processed, that is not virgin, that doesn't come out of a production facility, that you have no idea what's the strength, right? So assessing this is something that we've been looking into right now. We've been preparing a publication, will be out in a couple of months, where we've been conducting tests on this material that we basically reclaim from facilities, and how we can predict the capacity. Stock-driven design, as I just shown, I think that's going to be more and more relevant. Like, how can you design from availability? That's relevant for timber, but also for other materials, because it's completely different workflow, right? When you design right now, you absolutely don't ask yourself, in a traditional sense, what kind of material is available. You just do your design, and that's a secondary problem. But if we are serious about reclaiming and being circular, well, we need to change that. And of course, robotic fabrication, which is kind of the topic here. It is essential for automating this, but automation is not a necessity per se, just because it is cool or just because looks like an advancement in technology, but actually it is an enabler, because as you see, some of these structures are absolutely complex, and that's also something that allows us to make sustainability or sustainable construction and kind of optimized construction sustainable in terms of time, in terms of money, in terms of resources that you use. So these are the key 3 points that I wanted to deliver to you, and I want to thank you for your attention.
Well,
Thank you very much, Roberto. So this is part. We invited Roberto, so we thank him for coming. So this is part of a collaboration between our lab here at Rio de Janeiro Federal University, LAMO, and we are bringing Roberto together with Capsprint, so the founding agency for internationalization of Brazilian construction. I will speak also in Portuguese for you to help with the questions. So we also want to thank our partners. We have a robot down there, so most of the team here is working on this workshop, but some other freshmen and first year students. Now I switch to Português. Então, pessoal, obrigado por virem. Eu vou ajudar aí também em algumas perguntas. Eu acho que, primeiro, agradecer aqui ao Roberto. É uma perspectiva muito diferente aí da nossa construção, né? Eu acho que a parte aí que também é interessante para vocês verem é que a gente pode falar de ecologia e tecnologia ao mesmo tempo, que é uma coisa que a gente aqui fica achando que os computadores é uma coisa e depois constrói ali uma barraca ali do lado só com madeira e não tem nada no meio. Então ele está mostrando aqui que podes ter várias formas de colaborar e no caso ele está utilizando para reutilizar madeira e é uma coisa que a gente pode pensar também de outra maneira, porque a gente eventualmente não tem esses recursos todos, mas existem maneiras de juntar tecnologia e investigação e construção. Então aí também falar aqui, agradecer também aqui ao Pedro, também é parceiro nesse projeto. Na pressa acaba também agradecer também ao Prourb, porque é uma leitura incluída no Capsprint, mas vamos lá aqui nas perguntas. Matias.
Roberto, thank you for the presentation. And what time you get this project? How much time you work in this project to finish?
So how long does it take to finish one project?
There's 3 projects.
Well, I mean, it's a bit cumulative. I think I maybe could understand.
What he's asking, how long are you doing this?
So I think all of these projects are from the last 5 years, with other projects as well. And so these are not the only things we do. So this is like a selection, try to make sense for this lecture. But roughly, some of the projects takes maybe 6 months, especially the initial ones, because you're trying to figure out actually both what is the problem, and what you're looking for, right? You follow a principle. But then if you see they're kind of iterating, and we try to be including other aspects. So for example, the recompute system that I showed to you before, this is now the result of 4 years itself of study. And it is, I mean, we find it now kind of major to go out of what we call basically like research development to go into innovation. So how can we make this possible for the outside world, for the industry? And then of course things will change. But I think normally, just to try to answer the question, I think it takes between 3-4 years from scratch from a topic to go to a level where you find it mature enough to be transferred to construction. But depends where you start from, right? Especially how ambitious you are with your research question. Yeah. Did I answer the question? Okay.
Also, this research is done in the university. This is important.
Yeah.
Essa pesquisa é toda feita na universidade, tá, gente? Não é quando terminou, não é quando foi fazer um master, não. É feito dentro da universidade com pessoas que também estão num nível inicial e outras mais avançadas. Bom, deixa eu passar aqui.
Hi, Roberto. Thank you for the lecture. That is amazing. I had a question is about when you said about voxel clustering, and you're saying the voxels store information, and I don't know, I was a bit curious on how that actually works. How does the voxel store information in that sense?
That was the coding.
So why voxels? Is just a convenient way of structuring data, I would say. So when you have structures with so many elements, it becomes computationally inefficient, and you want to generalize to some extent, especially if you want to run some simulation. So that came out of a necessity of using these simulation tools, and basically kind of finding as in-between discretization for these structures. So a lot of the simulation we do, they are under assumption that these are of continuum mechanics, so these are the continuous stresses. And then the question is how you discretize this. So the voxel became a kind of in-between way of running analysis and keeping relatively abstract, so that we can do design iterations there. Now, actually the projects kind of evolve how we do this, but essentially the idea is that we try not only to use it as a two-dimensional block, but also try to evaluate the stress field locally and in the specific voxel. So we basically cluster information, not so cluster, we actually store information at the voxel level. The clustering is when different voxels are actually having the same attributes, they're actually clustered together. And that becomes basically a continuous element. That is the idea. And that's very important if you want to have design iterations that are kind of quick. Of course, this has a lot of potential for implementation with other machine learning techniques, for example, right? Because that becomes a way that you can process data much faster, right? But that's something that is not shown here. Yeah, and thank you for the question.
Vitor?
You say so about this discretization as a way of storing data,
Yeah.
but there is also a side of aesthetics of how these discrete structures look like. Very different from this smooth, white surface that were so common in the 90s and 2000s. Do you think about the role of aesthetics in these discretized structures, or you are not interested on it? Or you rather do not talk about that?
So yeah, I think all of the three are. Actually, I never speak explicitly about aesthetics. So I always try to speak about what is scientific content, technical content. I see aesthetics more than a result, like a method, like, I don't know, if you are an engineer or a mathematician, like solving elegantly basically what you're doing. So I think it's part of the method that you use in processing this. And I like to quote always Buckminster Fuller that says that if you have a steady process, then beauty will come out of it as a result, right? Because you have actually follow a very consistent workflow and so on. So that's a little bit of philosophy. But yes, you're right. I mean, there is I don't think all of the project looks the same, but there is something about using different parts. And I think it's somewhat the result of the workflow that we use, the tools that we use, but also the fact that eventually all of the timber that we're using is engineered to some extent. So these are already, like the timber that we use every day doesn't come in the form of a log. It is already sized to certain, and normally square to some level. So I think it comes from a realization of that. But now, when we go back 5 years ago, yes, the question was like, how do we actually make like digital timber architecture look in digital? So a lot of this process is like questioning basic workflows and trying to understand what would be the material, let's say, correspondent for this. And I think that's also why we started looking to voxel, maxels. This came a little bit of answer to that question, because a lot of timber construction you see these days are, as I showed before, it's just CLT mass timber put together, and then it doesn't tell you anything about the process. Now, some years after, I say the process is important if it's efficient, if it's sustainable. If it's beautiful, it's better, because then you can do more things. But I think it comes from the fact that we work with high resolution. So that's why we do that, is to save material and to be more precise in what we do. So yeah, I think it's not something that we pursue when we start a project, but it's more like a methodology.
Well, so Roberto, you're not afraid of making ugly buildings or ugly solutions in a way. So I think this is kind of provocative, but Roberto is opening ground for different kind of explorations. But we can also think about other algorithms that are together used with optimization that could analyze the beauty of the results. And if we are talking about artificial intelligence, for example, this could be one way of, and also we will see some work with Victor using AI to choose aesthetic qualities. So just trying to close the conference and to thank Roberto for his personal effort and development through the years, and we can do other questions later. But meanwhile, there's a workshop on robotics going on, so thank you all, thank you Roberto, and we'll keep up doing stuff, and thank you everyone.